Good morning. Today we're going to be talking about polar and nonpolar bonds. Now, I know you have heard the word polar and nonpolar before. We've already categorized what a polar bond and a nonpolar bond is when we looked at electronegativity. But here we're just going to be talking about in a little bit more detail what exactly polar means. It's a pretty important concept, and it's one that's going to come back again in grade 12. So we're going to talk about exactly what a polar bond is. So what we're going to start with is just a little bit of a review. So I actually don't want you to add this to your notes at all. You don't have to worry about copying any of this down. This is just going to be a reminder from grade 9 and grade 10 how ionic and covalent bonds work. So ionic bonds are formed with the electrostatic attraction of a positive and a negative ion. So essentially we have a sodium here that's lost an electron. That means it's become positive. We had a fluorine here that gained an electron. That means it became negative. So the fact that this is positive and this is negative, we actually see an attraction between these two ions. So in this case, we've actually seen the gain of an electron as well as the loss of an electron. So fluorine gained an electron, sodium lost an electron. So ionic bonds are formed through the exchange of electrons. A little bit more about ionic bonds. So the atom that is going to lose the electron is going to become positively charged. So the atom that's going to lose is always the one that has a lower electronegativity. So whatever's on the left-hand side of the periodic table, right, based on the periodic trend, whatever's on the left has a lower electronegativity. That's the one that's going to form the positive. That's called your cation. And whatever's towards the right of the periodic table, that's where your electronegativity is higher. Those are going to gain the electron. Since you're gaining an electron, you're negative, you're going to be called an anion. So cation is typically the metal, anion is typically the nonmetal. Now let's talk a little bit about covalent bonding and how covalent bonding works. Covalent bonding, we told you in 9 and 10, occurs between two nonmetals. The reason that covalent bonds are different from ionic bonds, we're looking at electrons sharing rather than electrons being transferred. So I hope now that we've actually drawn these diagrams, now that we've drawn covalent bonds using Lewis structures, you understand this a little bit better, and you understand that it's not a transfer of electrons. It's really two atoms that are sharing an electron pair or two electron pairs or three electron pairs. So let's take a look at two fluorines here. So each fluorine has 7. That means this fluorine wants to gain 1. This fluorine also wants to gain 1. So neither one's really willing to give up their electron. So again, what's going to happen is they are going to share this pair of electrons. This electron is going to spend some of its time over here. That's going to make this fluorine happy. And this electron is going to spend some of its time over here. It's going to make this fluorine happy. So a covalent bond is formed by the sharing of electrons rather than the actual transfer of electrons. So you can see here that this fluorine is going to have 8 electrons when this electron is spending time over here. And this fluorine is also going to have 8 electrons when this fluorine is spending time over here. So that's a review of what we talked about in grade 9 and 10 bonding. Now we want to talk a little bit more about how electronegativity comes into play with polarity. So we've already talked about electronegativity a little bit. Let's go ahead and let's apply it now to polarity. So we're going to talk about what's called a nonpolar covalent bond. So a nonpolar covalent bond, we've already classified these. Nonpolar means that it's not polar. So what happens in a nonpolar bond? You have electrons that are shared between two atoms. That's forming your covalent bond. In most nonpolar covalent bonds, the atoms are usually identical. So for example, chlorine here is two identical atoms. We have a chlorine atom here. We have a chlorine atom here. So they are the exact same atom. That means they have the exact same electronegativity. So essentially what that means is I always like to think of it of like a tug of war. So you have a chlorine here and you have a chlorine here. And since they're the same atom, they have the exact same strength. They have the exact same electronegativity, and they are fighting over a pair of electrons. right? So they're fighting over a pair of electrons, and they're working on this tug of war. Now, this chlorine and this chlorine are the exact same strength. Since they're the exact same strength, there's going to be no winner, right? The electrons aren't going to be pulled more in this direction. They're not going to be pulled more in this direction. Instead, they're just going to spend their time equally between them. They're going to stay right in the middle. So since the electrons are spending equal times between them, we say this is a non-polar bond. We say the electrons are being equally shared. So now we're going to talk about polar covalent bonds. So with a polar covalent bond, we actually have two different atoms. So for example, we have hydrogen and bromine. Since we have two different atoms, the sharing is actually going to be unequal. So we see hydrogen here on the left. Hydrogen is weaker. It's got a lower electronegativity, so it's got a weaker hold on those electrons. Whereas bromine on the right is stronger. It's got a higher electronegativity, so it's got a stronger hold on electrons. So they're still in a tug of war, but now we have a weaker atom and a stronger atom. They're not equally matched, so the stronger atom is going to win. It's going to pull those electrons closer towards that stronger atom. Now, let me be clear, this is not an ionic bond. This atom isn't strong enough to actually steal those electrons, right? They're not going to permanently come over. Just going to mute that there. They're not going to permanently come over, but they are going to spend more of their time here. So what that's going to mean is it's going to mean a slight negative charge. That's what polar is it's a slight charge. So we kind of use this weird kind of figure 8 symbol here with the negative sign to show that bromine is going to be slightly negative. The negatives are spending more time on this side. It's going to cause a slightly negative charge. On the other hand, that means the negatives are spending less time on this side. Since the negatives are spending less time on this side is going to be slightly positive. Just to reiterate, this is not a complete transfer of an electron. So you're not going to see that electron being totally transferred. So for example, here we have a hydrogen fluorine bond. The electronegativity difference is big enough to make it polar. That means that the electrons are spending more time with fluorine. They're not completely transferred. This doesn't become an ion. It doesn't have a permanent negative charge. We're not going to put square brackets around it. We're not going to put a negative up here. It just means the electrons are floating more towards this side. Whereas in chlorine and chlorine, again, they have an equal strength. That means the electrons are floating right in the middle, and we don't have a charge seen at all. So when charge separation of this type is present, we call it an electric dipole. So we've used that word dipole before when we talked about dipole-dipole. A dipole just means that there's a charge separation, and there's a slight charge on one side and there's a slight charge on the other. We also call this a dipole moment. So it's a dipole moment when the electrons are spending more time towards one atom, and therefore we call it a polar covalent bond. Polar because there's a dipole moment, there's a slight charge. Whereas with nonpolar, there's no slight charge, there's no dipole moment. So again, let's remind ourselves of this beautiful little number line here. So just a reminder that anything greater than 1.7 is ionic. So anything on this side here sees that transfer of electrons. Anything 1.7 or less is considered to be covalent. So that's that sharing of electrons, not the transfer, but the sharing of electrons. We again then divide this into two different categories, right? So that dividing number here is 0.4. And under 0.4, we say that anything that's less than 0.4 is nonpolar covalent. Anything that's more than 0.4 is polar covalent. So on the nonpolar covalent, it's not always actually atoms that are the exact same. It's typically atoms that are the exact same. You can technically have two different atoms form a nonpolar bond, but their electronegativities have to be very, very, very similar. They have to be almost the exact same strength. Their electronegativity differences have to be less than 0.4. Polar covalent is when you see that bigger electronegativity difference. So you see one atom is stronger than the other. That's when that difference is between 0.4 and 1.7. And then when you get over the 1.7 hump, you actually have an electronegativity difference so big that you can actually see the electrons be stolen. They're actually transferred from one electron to the other, or from one atom to the other, and that forms an ionic bond. So just in terms of a couple examples that you might see and how you would actually represent them. So for a nonpolar covalent bond, again, they're typically two atoms that are the same. We have bromine and bromine in this case, and those electrons are right smack in the middle, so therefore we don't show any dipole moment. In polar covalent, we do have a difference in electronegativity. So you need to figure out which atom actually has the greater electronegativity using your chart. In this case, chlorine has a greater electronegativity. So we put that weird little kind of figure 8 missing an arm, that dipole moment, and we put a negative here because the electrons are spending more time with chlorine. On the other hand, for hydrogen, we still have that dipole moment, but it's positive in this case because the electrons are spending less time over there. And in an ionic compound, you actually see the transfer of electrons. This forms a permanent ion. So you have your cation, your positive, and we use square brackets to show that it's an ion. And you have your anion, your negative. Again, we use square brackets to show it's an ion, and we've got that negative symbol there. Typically, rule of thumb, but we do use electronegativity differences. Typically, ionic compounds are between metals and nonmetals. And then typically, polar covalent compounds are between different nonmetals. And typically, nonpolar compounds are between identical nonmetals. So that's all that you have to know about polarity for grade 11. I do want to put one more piece here though as well too, and that's going to be what you're going to learn in grade 12. So there's also something more that matters for polarity, and it's symmetry. So polarity is also going to rely on symmetry, and it's going to depend if two dipoles are actually pulling in opposite directions. So I want to show you this now, just that way it doesn't kind of blow your mind in grade 12. And if you don't get it, no big deal. We don't deal with it to grade 12, but it's something to kind of think about. So I'm going to go ahead and I'm going to draw ourselves. It's great practice to draw Lewis diagrams. I'm going to draw myself carbon tetrachloride. So we're going to draw ourselves. Carbon has 4 valence electrons. Chlorine has 7 valence electrons. So again, this is great practice for drawing Lewis diagrams as well too. So we have to determine which one is going to be the central atom, which one has more bonding potential. In this case, carbon wants to form 4 bonds. Chlorine only wants to form 1. So we're going to go ahead, we're going to put carbon in the center, and we're going to put its 4 electrons around it. And then chlorine, we're just going to arrange chlorine on the outside. Now remember, I cheat. So what I do is once I get the chlorines arranged, I'm going to put their free valence electron towards the middle. So I'm going to put the free valence electron for chlorine towards the middle. I'm actually going to put it over on this side. I'm doing that on purpose, I promise. I'm going to put, oh no, shouldn't have done that. I'm actually going to put it on this side, and I'm going to float that electron from carbon over here. Again, I'm going to put that free electron for chlorine here, and I'm going to erase this one here, and I'm going to take that free electron for carbon, and I'm going to float it over here. And I'm going to put chlorine's free electron here, and I'm going to take that electron from carbon, and I'm going to float it over here. And same idea, I'm going to put chlorine's free electron here, and I'm going to take that electron from carbon, and I'm going to float it over here. So we can see that we actually have chlorine is going to be full. Chlorine's going to have its other electrons around it. So chlorine's going to have 8 valence electrons. This chlorine is going to have 8 valence electrons. This chlorine is going to have 8 valence electrons. And this chlorine is going to have 8 valence electrons. So carbon here has 1, 2, 3, 4, 5, 6, 7, 8 electrons. Now, why did I kind of put those electrons so weird where they're floating away? Because the electrons are going to spend more time with the electronegative atom, and the electronegative atom in this case is chlorine. So those electrons are being shared between carbon and chlorine. They're just going to spend way more time with chlorine. So chlorine is going to be considered to be slightly negative, and chlorine is going to be considered to be slightly negative, and chlorine is going to be slightly negative, and chlorine is going to be slightly negative. So we have a bunch of slight negatives here. Now, this is where symmetry actually comes into play because now we can almost think about it as a nice long tug of war. So, this side we have a chlorine, and this side we have a chlorine, and these two chlorines are totally identical. So, what's going to happen is these two dipoles are actually technically going to cancel each other out. So, since we have a chlorine pulling in this direction and a chlorine pulling on this direction, we actually have two atoms that are the exact same strength pulling opposite each other, and it's actually going to cancel out that dipole. And then these two chlorines here, same idea. We have a chlorine and a chlorine. We have two atoms that are the exact same strength on either end pulling on each other. That means they're going to go ahead and they're going to cancel each other out. So when you have symmetry, that means you're equal on all sides. When it looks equal on all four sides, this is an example of something that we would think would be polar, but carbon tetrachloride actually shows non-polar characteristics. That's because your dipoles are canceling out because you have two atoms on either side of equal strength. So that's what we're going to cover in grade 12 for polarity. Not too complicated. In grade 11 chemistry for polarity, all I care about is it polar, is it nonpolar, based on the electronegativity difference. Now we understand everything there is to know about how bonds form. And now we understand actually how to draw those bonds. So we understand with Lewis diagrams how to draw ionic and covalent compounds. Next thing we have to do is we have to talk about how to name those compounds. So we're going to go back to reviewing grade 10 chemistry. I know you're all very excited, and we are going to review how to name ionic compounds and how to name covalent compounds. So that's where we're going to go with the rest of the unit.